his research about a novel hybrid approach for simulating Airbus events. And it's gonna be a really exciting presentation. And before his presentation, let me briefly introduce Ian Lee. Ian Lee is a PhD candidate at the University of California, Berkeley, advised by Professor Panos Papadopoulos. His primary research area is understanding the thermomechanical behavior of highly heterogeneous material using computational homogenization. In addition, he is interested in utilizing data science techniques to develop efficient surrogate models for complex physical phenomena. He completed his bachelor's degree in civil and environmental engineering with a minor in computer science at the University of Illinois at Urbana-Champaign in 2020 actually. And without further ado, Ian, please start your presentation.
Hi everyone, I'm Ian. I'm a PhD candidate here at Berkeley, and I'm thanks Shan for the wonderful introduction. I'm a biotech professor Panos Papadopoulos, and here in this next 30 minutes, I just kind of want to present a little of my research, what I've been working on this summer, where I was interning at Lawrence Livermore with the Planetary Defense Group under the bigger strategic deterrence umbrella, where I was advised by Veronica Korniava and Evan Bionis. There are two postdocs there that I worked with this summer, where I have developed a novel hybrid approach for simulating airburst events. To kind of open up to kind of physical understanding what exactly is airburst event or what's happening here. We can think of these airburst events or what happens when a meteorite enters the Earth's atmosphere and start burning up, and they're burning up, they're depositing energy along the trajectory. This energy now deposited now can generate stuff. There's new physical phenomena such as shock, right? These kind of things. Flat. And for this particular picture we see here is what happened in 2013 in Chelyabinsk, Russia, where we have a bolide about 20 meters in diameter went over it. It released about 500 kilotons of TNT. In the labs talk, they will immediately go and talk about how Nagasaki is only 32 kilotons, so this is something huge, and we got to pay a little bit of attention to it. Or, if we're here in Berkeley, you can think about this as, somewhere between a magnitude 5 and magnitude 6 earthquake. So, we got that retrofit up on the stadium up there too. So that's a big thing. When this happened in Chelyabinsk, caused over 1,000 indirect injury. You can see with the blast, as the blast emits, windows shattered, and more than 7,000 building damaged there. So this is some phenomenon we kind of need to have an interest in studying. And this is actually a very interesting phenomenon because it's a very physics-rich phenomenon. On the onset, you can see this is a fluid-solid interaction problem as the bolide travels into the atmosphere from space, and it goes streaming through the atmosphere, and it's streaming at hypersonic flow velocity. So here, a lot of our physics start breaking down. Your gas dynamics, standard gas dynamics, no longer apply. Your ideal gas law fails because now you have additional energy modes that you need to track as your particular, air particles have vibrational and rotational modes, and you need to track for their equational state. And for the solid, we're also dealing with a complex problem here, right? Not only is as the bolide is burning up, it's breaking it. There's a fragmentation problem, and we had to look at how these kind of more, some more organic rocks versus some more metallic rocks have a wide range of material properties that can govern how this fragmentation occur. And there's some little samples here that we presented from, Chelyabinsk and different asteroids that crashed down, and we do take in them to get property. And combine them all together, this is also a data spark problem. First Chelyabinsk photo we saw happen in 2013. The next one we have in 1908 in Tunguska. So we're not exactly here working with something we can exactly replicate in a laboratory, get a lot of data points capturing. So hydrocodes such as CTH or E3D, both developed in India and Lawrence Livermore, are kind of our best bet at kind of understanding, hey, what happened when a rock travels at hypersonic speed, going through the atmosphere, start breaking up, because we're not finding a laboratory where we can shoot these rocks like that. And for this particular project, I'm actually working with, moving out the finite element world and into mesh-free land of Spiral++. Spiral++ is a smooth particle hydrodynamic code developed at Lawrence Livermore National Lab. It's an open source, parallelized, And in fact, the group I'm working with have developed a particular fluid solid interface solver that there to kind of work with material with dissimilar density, right? The air and the bolide density are going to be extremely dissimilar. And SPA, traditional SPA have some sort of limitation trying to struggle between how to reduce artificial surface tension. So going back to jump to the gun, that's just photo being played in here. This is the SPH simulation of an asteroid going circular of a spherical asteroid going through a bolide as it breaks up. And I put it on loop. You guys see it expand. I think Shen put that on the poster for everyone to see here. And that's cool and all very well done as spheral. But as we all know, hydrocos have a catch. And the catch is, it's expensive. That particular three-dimensional simulation to solve took about more than 1 million CPU hours running, cranking out, that's why Livermore had their own little power station and water cooling station there to support their little computing facilities there. And even for like a 2D dimensional simulation where you just have one set of inlet conditions, sitting air particles screaming here, hitting a particular bolide solid here, this particular simulation still take about 10,000 CPU hours. And you guys, people who are a little bit more clever, might see a little reload here because I actually had to run a restart file on these guys here because they don't even run in full 24 hours here. So, but these emulations are great because now they're high fidelity. We're tracking both materials simultaneously, but sometimes we might want something faster. And this is where we can kind of take advantage of looking into the physics and kind of trading away fidelity. We don't need to have the most high fidelity simulation while we can have some acceleration in our computational speed. Here, we're kind of, there folks have done this before. I think Ruko from MIT actually have done this before where they, instead of explicitly simulating the whole bow shot that developed from the bolide, we are able to kind of use the whole gas dynamics by replacing the bow shot with a surface traction force. That now turns this entire, before that was a full fluid solid interaction problem. Now this is turned into almost like a compression task. The fact I'm saying it was noted that it almost at the start, still under linear elastic regime, it started looking like a Brazilian disc compression test. It had the exact same kind of stress forces where you have now the body force fixing in, surface traction force compressing the body. And this simulation run a lot faster, under CPU hours, and a lot faster. But as you know, I notice here, this particular deformation mode looks a lot different, right? We start getting the tips to shred off, and this whole deformation mode no longer looks the same. And that's because this is what happened when the particular assumption that led us to replace the surface traction forces are failing. As the disc started to undergo finite deformation, higher order effects started to kick in, and we can no longer do such an assumption. And my goal for the summer was to develop a physics package that we can take advantage of this lower order simulation. We can run this compression test, develop some sort of hand-on techniques, such as, hey, what if I ran this for 2 seconds? What happens if there's 1% kinetic energy loss? And once I have some sort of criteria to decide which regime am I living in, and is my, nice surface traction assumption broken down enough, I will transition this simulation into the higher order or the full fidelity model where I can have air particles running in, kind of more accurately capture this particular shape, those bow shot development. So, and the summer I spent a good 2.5 months trying to develop. And the first thing here is there's kind of a picture to keep in mind is that both the solid only Airburst and the two-phase Airburst have already been developed there, and it's kind of individual scripts. But those two scripts doesn't talk to each other. And sure, we can kind of just clutch them all together and just have, mysterious functions within a function, within a function, within a function. That's not very productive, and there's a lot of bugs, and you start sitting there trying to trace down. Why am I getting a memory out of bound here? What's going on here, guys? So a big part of my effort initially was kind of writing kind of a hybrid setup script where I'll have the air node sit on the left-hand side, patiently waiting. Well, initially we'll apply surface traction force on this particular solid bullite, and getting compressed like elastic little ball. And once I get my handle condition, whatever that might be, I will let the air nose come in. That and a slower animation look like this, but this particular animation actually has a lot of detailed physics here, because not only we need to make sure have the transition happen, we need to make sure this transition happens smoothly. Because you can imagine you're suddenly releasing off all that supposed surface traction forces, then these air particles traveling at hypersonic speed, hitting your particular bullite. That particular thing will cause a lot of unphysical or unwanted physics. Got a lot of rating effect. Your bullite start blowing up mysteriously during simulation, and you just get to look at an empty space on your whatever visualization software of your interest. Now that's kind of what happened is that we take advantage of what already been developed, which is called soft start, which is instead of having the air particle comes in at hypersonic speed, you slowly ramp up the particle. But here, not only do I slowly ramp the particle as it travels over to hit the bullite, but it kind of slowly envelops the bullite. I also need to slowly remove the surface traction forces that was initially simulating. But at this particular point in the transition region, it's actually very sensitive because not only I'm slowly releasing off the surrogate forces that we're using to kind of predict what the bull shock is doing, I'm also having me to have the air particles slowly develop around the bullite without causing any additional damage. And a lot of things that could have gone wrong here is that what happened when you send the air too hard? Because SPH is a mesh-free method, there's no reason why the solid nodes should push the air nodes out. You can get air nodes embedded themselves in front of the bullite here. This is the picture of the pressure visualization. You can see the nice bull shock developing, and then we see almost little cold spot occurring in front of the bullite after handoff. And that's because these air particles just got shoot out the gun, get smacked between two solid nodes, get themselves embedded in there, and sooner or later these low pressure fields don't cause everything to blow up after simulation. We now have little not hot spots but cold spots in the front. And that's where
what's your traction model?
Ours?
Is it just a Roby square traction model?
This has been Asperger's strain, and we just put fold with a K wine bowl.
What's the formula? So if you say, hey, I need to know a traction on this surface, what's the formula you use?
We put forces on the so the solid only model, we put the traction forces by calculating forces on the particles. So
But what is the formula for those forces?
that will be the gas.
Is it just like a Roby square?
Roby square, yeah. The modified Newton series, Roby square. We have the modified Newton.
Is there a correction for tilt?
I believe so. And I think we kind of use what Recode did. They do it or find elements and we kind of took whatever they did for.
And when you replace the traction condition with incoming particles, there's not too much of a jump.
Not too much. That's why we had the smooth. We want to have a very smooth transition. Try to adjust it there. We don't have all sorts of artifacts that could develop. One time I had to release it too fast. I get a ring.
Yeah.
I could see like a stress wave developing from the inside out, and then now it's bow shock and the stress wave. That was not good.
Yeah.
So that's kind of what happened. And part of this is to say that the FSI SPH formulation developed a little more pathways to kind of create almost a surface force coefficient to prevent interpenetration. This is another numerical artifact where at the onset of the contact problem, we can turn on almost like fictitious repulsive forces that prevent air nodes from getting in. But those need to be used very power, very responsibility, blah, 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 things. And then you're here trying to fix one problem, you're going to break something else later. And I'll show you what happened when I break something else later because I ran out of time and the computing system, the Livermore I was working, had the fire alarm pulled on this. So I couldn't compute anymore. So hang on that thought there. So here, let's do some kind of validation here. I did a full 2D geometry simulation where I put a manually transition, the black dotted lines are manual transition time period, with entry angle of 45, initial velocity of 20 km/s, and a bullite radius of 25 meters. The blue curve is the hybrid model that have after the capture handoff, where it usually starts off running here was the solid only model, and then transitioning to the fluid. And this blue curve took about 2,700 CPU hours to complete, a lot faster than our full scale simulation. Now you can see that we're this is kind of an initial benchmark. We put a very conservative transition, right? We don't see any of the major curve diverging away from the kinetic energy losses of the body. But here we can see in the long term here, as the bolide drops down to the atmosphere, the yellow curve, which is the solid only curve, the lower order model significantly start to diverge away from the hybrid and two-phase model. And that's only good to catch that, even though it does not align, these are a lot closer, and we're still getting a very big computational gain on our simulation. What is more exciting if you kind of look at what the normalized energy deposit rate curve. That is the interchange in energy of our predicted simulation. That's what we can think about what's energy this bolide are releasing to the atmosphere. And what's exciting is that we're able to even capture the very similar characteristic utility bumps, because the hybrid method was able to correctly capture the fragmentation mode. So we have the correct energy deposition, whereas the solid only, it just kind of goes straight off and have a complete. And to kind of animate that, we have the lower order solid only simulation, hybrid simulation, full 2-order scale simulation, all running in tandem here. And we can see here that this fragmentation is starting to fragment a lot earlier, and doesn't have that same pancaking bending over and then breaking up. And that's kind of a big thing. What we were able to do correctly was that we were able to get the hybrid method to have the same breakup mode as our full fidelity simulation. And remembering that fictitious surface, the arched surface force we're talking about, most of us keen eye might see that after transition, we start seeing a little line of damaged particles sitting here. That is caused by that repulsive force that we're here to prevent air particles to get in here. So that the little kind of damage there is also another artifact that probably need to be fixed later on, but at the time we ran out. And that kind of leads to the conclusion here, where we hate that through my summer work at Livermore. I really appreciate them for giving me the internship opportunity to develop a novel hybrid civil physics package that can kind of take advantage of both the speed up from a lower order physics model, from a lower order model, and also while retaining the fidelity of a higher order model. And kind of now the kind of semester that I'm kind of still currently working on. Initially, we're hoping to apply this to 3-dimensional simulation, but computing resources are a little bit competitive, so that's kind of on the back burners a little. The other thing here that in the particular benchmarking initially during an internship, I really want to look at 2 particular handoff conditions. One is the time. I pick a time in the simulation and I hand off there. That's not very realistic and a more generalized or modularized setting. Second thing I picked was kinetic energy, and that's the most conservative kind of handoff condition they can put out there, right? That's kind of thing that, hey, if my little bolide had lost enough mass or lost enough energy to travel away, I think I have to have some sort of significant deformation, so therefore I need to hand off there. To particular, because we're all at least I'm mechanical engineering here, that we're taking, interested in this semester kind of to postulate what would be kind of a strain-based approach, and and what would be a kind of a strain-based approach to kind of look at how much this bolide had to form. Some potential software we've been playing around with is kind of using sphericity to see how much, at least for circular bolides, how much the sphericity of the bolide had, degraded. That might be a particular thing handoff, right? As it, become pancaking and start bending. Maybe that'd be a more aggressive handoff that we can use to play around with. Another one is kind of our stress-based. We're thinking about what can be a possible stress-based approach for handing off a particular simulation. And for the stress-based one, that kind of motivate back to kind of the initial Brazilian disc test, right? We have a diametric compression test. And trying here, we'll be trying to find kind of like a few soft I have right now, to kind of take a look at kind of what would be the effective stress on the bolide and what's the ratio between the compression and the tensile pressure. And maybe that would be another catch that potentially that can be used to be can off. And yeah, with that, I think that's gonna be my presentation. And any questions?
Right. So just now when you, one of your video in the middle, there is like a jump,
Which one?
the stream video. So the middle one doesn't have any airflow, and then suddenly there is an airflow walls. Part like that.
This one?
Yeah.
So this airflow initially was we were only running a solid hole. So all the air was pulled up onto the left-hand side. But we still had to have air nodes initiate in the simulation at start to be program implementation. That would
I mean, what I'm trying to say is that, so you only push air at the actual center.
Yeah. Only when we say we are handing off, then the air get pushed through. Or else the air just sit here. In this simulation right now are matching. Because we only have traction forces until the handoff condition, then the air nodes can then enter the high fidelity simulation.
So on the second simulation, when you see the damage particles with the, it does come from like the initial impact with the.
These guys came from the initial damage of the airflow. These guys are from the bow shock. The back is correct. Back is the more physical damage because you now have a bow shock in the front, and the thing began to compress.
But why this side doesn't have the initial?
This one?
Yeah.
So this one we were able to initiate the airflow at a very early on. So and also when this bolide, we initialized the airflow initially, this bolide had not undergone damage. So this was having a higher strength, so I didn't need to play with the surface force coefficient. Here, when we drove the handoff, I actually had to tune the surface force coefficient higher because the bolide have already been damaged, the weaker bolide, so I need to have some sort of repulsive force to be put on the leading edge to ensure no penetration. But that requires a little more calibration to make sure there's no damage developing based on. That's why we see damage develop front and no damage develop this particular front. Because this bolide starts was no damage, this bolide started was damage.
Good question. When you do SBS, are there any limitation for simulation of the Airburst? When you do SBS, are there any limitation as compared to another method like CFD or?
So limitation on that question. I will say SPH has a very sensitive. It's very sensitive. All formulation are very problem dependent sensitive. In trying to get more physics from the mechanic side is very challenging. For example, porosity, right? Each of these nodes has some sort of microporosity kind of parameter that goes in there to kind of affect the effective property. That's very iffy. That's a very iffy thing. So I did not play any of it. I just hear about that's a challenge there. I think, and also it is a mesh-free problem. So, you get some gain on a fracture problem, but you also lose some gain on, right? And I think the biggest thing would be that the initial solid only simulation is actually a lot more challenging to set up, right? You might think that a virginity disk test might be your standard, two Dirichlet boundary condition type of problem you can set up on your finite element grid, right? But here, that's not the case for SPH, right? Because enforcing boundary condition SPH is very difficult. And what we had to go for here is that we end up having to have different rings of outer rings. And on each of these outer rings, we had to put on forces on each of the individual particles that matches the surrogate forces. So imagine the solid problem instead of just saying, okay, hey, I have some sort of forcing term. I had to go to each particle on top, put on a force calculation, and as it fractured each of these new fractured nodes, right? Each of these nodes that fractured off had to go and it's now gone into boundary condition calculation as well. So, right, and this other, so simulating this problem actually was a lot harder than, for the fluid here, we just need to keep resetting the reference frame and just have air particles shoot that here, right? This was actually a lot easier to do than this guy here. So that's kind of, maybe there's something advantage using finite elements here, as that might be easier Dirichlet problem, and then there's some sort of transferring between that might be of interest, but in this problem here, we just kind of did everything NSPH.
I think for the rocks or like all this asteroids, I think it's okay to use SPH, but I think what we're probably thinking is, why put the air model with SPH? Why you wanted the air as SPH as well? Because, for example, at the backside, right, you will have negative pressure, right?
Yeah,
That's actually
the
a
motion
very
price.
fast, like, yeah. So in SPH, if you have like, and density of the particle is really less there.
Yeah.
And particle, as you probably know, in SPH, the kernel was actually a function of the density. And if the density is actually, you have to somehow modify the
Yeah.
kernel. I'm not sure the pressure is correct.
That's a, yeah, so that's a, so from my best understanding of the ability here, and that this particular problem is fiddled to only match mechanical. This is pure, this is a very, I think, application to mechanical getting kinetic energy deposition.
No, but like the pressure, so for example,
Yeah.
something, the negative pressure.
Yeah, the negative pressure down here was the boat, in the weight, right?
Right, it will strengthen the materials at the back, right? Because it just give you
Yeah.
sort of like a push, like a push.
Yeah,
Instead of actually making separate, it's actually flipping. So I mean, I'm not sure whether you plot like so for example, there's one slide that you show of, is it horse? This one, yeah, here. Why the back color is white? I think it should.
those are what happen when there's not enough nodes there. There are no nodes for them to calculate the tessellation of the weight shot. Wait,
Oh, I
so this is,
But
but
this is
normally
like-
I visualize it with a particle point. This one I actually visualize with tessellation.
So it's like point for particle.
Yeah, point of particle, yeah. And there's no points in these regions.
Yeah,
where
exactly.
it's
This is what I'm trying to say, because in the regular air, everything is enclosed, right?
Yeah.
As long as it's really hard to create vacuum, because vacuum means like you're gonna suck all the air inside.
No, yeah, yeah, so. My understanding, at least from when I'm talking to the group, is that SBA has its limitation, and especially also. Even better, just hypersonic, here we're not actually even, we're still modeling this using, gamma gas law, but we're tuning down specific system. To get the correct pressure jumps here. I think the focus on a lot of these, this particular model is my understanding, but some are looked at, the goal was to get a very particular problem, having it to. More kind of an estimation of different angles and trajectory, and that this is definitely a limitation. I think that's why they even have the full setup of this FSI SPH, because again, like you said, that the silver material and all that, it's artificial surface tension. Going here, little pressure are going to cause a lot of issue. I think that's something we push through. But here, I think most of my understanding focus, they want to look at this for like a mechanical problem lens and having it go say, hey, I know what the kinetic energy deposition problem for letting asteroids that they can do when they do work with their. And that's the limitation of the model. Unfortunately, you get a very accurate 100% problem, but nevertheless, I can play around with being able to speed up for that. People can have some sort of couple.
But they don't have a CFD SPH.
What?
They don't have like a CFD SPH.
I think there's a DEM, someone's doing a DEM there on the fracture. I think it's most of the focus a lot more on the fracture. Side, at least from, but I know another person doing DEM on the asteroid, and a lot of it also for asteroid deflection, where they have some impactors with dark. So I think this particular step is a lot more focused on kind of an impact fracture type of setting here. And then fluid modeling. Or we're just trying to get the mechanical response for it. But you know,
I mean, like, I'm not saying that.
no, I understand. No, I mean, we're still using 1.4 gamma, 1. Gamma gas law out here in hypersonic flow. Like the whole fluid setting here is kind of fiddled to make it work for a particular application.
You know, I just wanted to say, I'm not saying that modeling with CRP or like finite volume will be easier.
Yeah.
Because then you have responding problems, right? And I mean, that's also another challenge. But I mean,
No, I think for this one, they were very much focused on impact, because it's from planetary defense, and they were mostly interested in deflection problems. So that's, I think, the motivation why they did it with SPH.
So we only saw one transition point here. Obviously, you're thinking about when that transition should happen, but have you tried others arbitrarily yet?
I ran out of time, and again,
Yeah, I was just
the
wondering.
fire alarm went off in one of the living computing buildings, so.
I mean, I don't know. This is also a problem for us at Geotech. We have a very similar problem with transitioning landslides, seismic landslides. A lot of people like to start an FEM, then transition to a displacement, say, method.
I know, I haven't got a chance to play a lot of different transition and the most of the transition has just been kinetic energy, time and geological improvement time. Was trying to play. That'd be interesting to teach.
Yeah, like,
Okay.
the thing is, like this, you have a straight line where you use translation, right?
Yes.
If you modify that time, the results will change.
Yeah.
And that's what you were.
Yeah.
Yeah. So.
But I didn't, yeah, no, I didn't, I only ran one
Yeah, sorry,
and 2
I think I
seconds.
misunderstood that comment. Obviously, you did make that comment before I started realizing it.
So
I
that,
think-
that line
yeah.
is shift.
Yeah, if I shift to different point. And I think they're gonna have a result for, I think one time I shift the very late handoff. The air comes in when like the
Yeah.
solid just completely disintegrates, the moment it comes in, and that's kind of where you.
Yeah.
We have a very, very conservative kinetic energy. I think it's less than 1% type of handoff there, just to be able to get it to. Have it a safely transition.
So then I think,
determine this transition.
This one, I kind of, well, this,
Oh.
I cheated because I ran both the full scale simulation and the solid only simulation. I put them up side by side for visit. I clicked through time step and be like, I think at this one, they still look the untechnical, and I think this as far as I can go out for this particular goal. So I picked, that's why there's this mysterious 2-second game pick, because I have already crunched out the true solution and been backtracking to see how well will the hybrid model perform. Because the hybrid model should perform well based on the handoff after I crunch the numbers like that, but yeah, I think what.
then I think, I guess, in relation to the other, how much does, so it's very nice, obviously, that the modes look similar in the long term. How much does it matter how closely they match? Right, I think is my question. Because I don't have a gauge of this problem for,
No, I also have very
yeah.
my understanding, I asked it to my mentors, and their response was they're all some sort of stochasticity inside their own fracture model where they
I see.
use like Ben Asper or Paul was like a
Okay.
line bolt
Yeah, yeah.
distribution. So there's some stochasticity there. So that the correct way would have been be do a whole stochasticity sweep and kind of look at an ensemble behavior. I think that's what
Yeah,
most
yeah,
published would have an ensemble behavior on the behavior.
I see.
I ran out computing research
Yeah,
to
yeah,
do
yeah, okay.
ensemble runs.
For
So-
sure, for sure.
So that's one particular explanation. The other one I was thinking it could also be that I have a slightly rougher transition, right? The pipe started off a little bit early. I don't know
Yeah.
whether that's because of the artifact that I was putting in to prevent air nodes from penetrating the bull. I'd have some sort of significantly hit back that causes this early fracture to be covered slightly earlier than because we did saw initial ring of damage developing in the front of the bull there.
Yeah.
So that's something as collaborator I'm trying to look into, but I haven't gotten a full.
Hey, thank you again for this fascinating presentation. Actually, the animation at the beginning reminded me of the Japanese anime Your Name, like the asteroid hitting the area. Like, that's very great one. And do we have any questions from Zoom?
The Zoom question. Let's see. Question. I don't see any. No.
I don't
Okay.
think so.
Cool. In the end, I would like to thank again thank you again, Ian, for this great presentation. I also would like to extend the sponsorship from the GA funding and the USAPM, just for the record. And yeah, thank you so much for coming for today's seminar. And yeah, we are going to have another one in November, and we'll keep you updated. And thank you for coming. And now we are going to have coffee hours. And if you have any questions about the presentation or about other things, please just talk to Ian freely. Yes, that's the end. Thank you.
How much do you save there? Your